If we are to use machine learning to generate or infer things about music, we will need data. But where is the data in music? Well, just like sound itself, this is a matter of perception. Our ears sense fluctuations of pressure waves, and our minds decode that as what we hear. These signals, or pressure waves, are continuous, meaning they are always happening and modulating. This is analog sound, a continuous signal in an analog world. In digital representations of sound, a sensor, like a microphone, is used to sample this continuous source tens of thousands of times a second. What it's sampling is the pressure at a very small moment in time. When you sample at a rate that's fast enough, you can accurately reproduce all sounds within the range of human hearing. These samples, when played back in the same order, can accurately represent sound sources and thus are a form of sound data that is probably the most concrete. There are machine learning models that take this data and learn from its patterns to either categorize or generate raw digital audio. Models like WaveNet and WaveGAN work on this type of sound data, and by analyzing sequences of samples, they can predict or generate the next sample. Similarly, other models can take music samples and report the pitch, what instrument might be playing, or even transfer a melody to a different instrument. But there is one important thing to note. What's referred to as CD quality audio is sampled at 44,100 times per second. This is a lot of data. And in order for a model to look at more than a few seconds of audio at a time, you need a GPU with a lot of RAM. So these models need some pretty high-end gear to run in a meaningful way. Luckily, raw digital audio isn't the only form of musical data. In the 1980s, digital instruments were becoming increasingly popular, and the manufacturers of these devices realized that they all would sell a lot more if each one could communicate with others regardless of what brand they were. Enter MIDI, the Musical Instrument Digital Interface. MIDI is far less information than raw audio, and is a very helpful form of data that describes musical events. An event is the moment something changes, like a new note being played or no longer playing a note, and usually includes some extra information about the event, like how hard the note was struck, technically referred to as velocity. So with just a few descriptions, or to use machine learning lingo, a few features of music as events, sound generators like synthesizers and drum machines can then be told what notes to play and how. One kind of funky algorithm that has brought machine learning into music is the Markov chain. Markov chains are state prediction algorithms. Not states with flags, but states like emotions, and actually much simpler states than that. In this case, the state is a MIDI note. This is a piano roll. It is a time-based grid that visualizes MIDI notes to be played as the transport, or the now, traverses the grid. So in a monophonic melody, where one note is played at a time, the pitch could be described as a state. If I stopped at any moment in time and asked, what is the state of the pitch? I could answer that question. A Markov chain is a type of model that traverses over a sequence like our melody, and each time the melody changes state to a new note, that change is recorded in memory. Once it has reached the end, every note in the training set of our melody has a place in memory, along with data about what notes came next. Let's zoom in on that. In this melody, a C was played 5 times. 2 times it was followed by a G, and 3 of those times it was followed by an F. Therefore, note C in our model has a 40% chance of being followed by a G, and a 60% chance of being followed by an F. And that probability distribution is what decides the output of a generative Markov chain model. It takes as an input some state, like a MIDI note, and its output could be any note that followed that state in our training data, picked randomly, but according to the probability learned from our training data. If you feed the output back into the input, it just keeps on ripping through the probabilities. Here's what that sounds like. Though we stay in key, it sounds like we are just a few steps away from totally random. Using additional Markov chains trained on other states or qualities of a piece of music, like the amount of notes played, the duration of the notes, the time between notes, and the velocity of the onset of the notes, we can make a much more comprehensive model that sounds like this. Or we can train our model on two pieces of music to generate music that contains the possibilities from both pieces. Some things to note about Markov chains. The melody can only ever transition in ways represented in the training data, and the melody can never hit a note outside of the training data. Notice the theme of some machine learning techniques' inability to do anything outside of their training data. Markov chains are referred to as a stochastic process, meaning that it isn't very precise and its predictions are maybe interesting but ultimately pretty random. What if instead of using just the current note, we looked at 2 or 3 previous notes? What effect do you think this would have on our randomness? The answer is that the more history our model considers, the less random the output will be. In fact, after incorporating just a few past notes into each prediction, the model will only replay the training sequence without any deviation. If you are into terminology, if we look at the 3 previous states to predict the next state, that is a Markov chain with an order of 3. And a quick side note here. In other algorithms, incorporating the past can be referred to as feedback, convolution, or recurrence. RNNs, or recurrent neural networks, are very common in musical applications of machine learning. Virtually all machine learning applied to music uses data not only from the current moment, but from previous moments. And thinking about music, does this make sense? Why is it that music is related to time in this way? Is it maybe because music is more about what changes and the degrees and the qualities of the changes? Of things like durations and dynamics? So in order for machine learning to learn more about music, it appears it must integrate time as a fundamental element.